All right, today we're going to decode the secret language that, believe it or not, builds our entire world. I'm talking everything from the tiniest microchips to the most massive skyscrapers. And it all boils down to one simple question. So, what do a microchip and a skyscraper have in common? I mean, really, think about it for a second. You've got this tiny little microchip, right? A total marvel of microscopic engineering. And then you have a massive, towering skyscraper, a giant of steel and concrete. What on earth could possibly connect these two things? Well, the answer is deceptively simple: measurement. That's it. Without the ability to measure things accurately, and just as importantly, consistently, neither of these incredible feats of engineering would even be possible. It is, quite literally, the foundation of everything we build and everything we understand. Okay, so if we're going to build anything, or even just study the world, we need a shared language, right? Before we can even begin to talk about things like motion, or forces, or energy, we have to agree on a way to describe the world, a way that everyone, everywhere can understand. And the foundation of that language is something called a physical quantity. It sounds fancy, but it's really just a property of something that we can measure and stick a value on. See, it's not enough to say a table is long. That doesn't mean anything. We have to say it's, say, 5 meters long. You need two things: a number and a unit. That right there, that's the whole game. But you can see the problem, right? If my meter is the length of my arm and your meter is the length of your leg, well, we've got total chaos. Nothing would ever work. So what the world really needed was a universal alphabet for science, a set of standard units that mean the exact same thing, whether you're in a lab in Tokyo or an engineering firm in Toronto. You know, the great physicist Lord Kelvin really nailed it when he said, "To measure is to know." And having these standard units, we call them SI units, that's what makes it all possible. It's what allows scientists to communicate, to collaborate, and to build on each other's work without getting their wires crossed. And here's the really mind-blowing part. This entire universal language of science, it's built from just 7 fundamental letters. That's it, just 7. We call them the base quantities. You're looking at them right now. Things like length, which we measure in meters, mass in kilograms, and time in seconds. Literally everything else is just a combination of these 7. So if those 7 are the letters, how do we make words? Well, this is how. We create what are called derived quantities. Take speed, for example. Speed isn't one of the original 7, right? It's a derived one. We create it by combining 2 of our base quantities. We take length, or distance, and divide it by time. That gives us meters per second. See how that works? It's simple, it's elegant, and it's understood everywhere. Okay, so we've got our language, we've got our alphabet. Awesome. But how do we actually do the measuring? I mean, in the real world. Well, it's all about choosing the right tool for the job. You wouldn't use a sledgehammer to crack a nut, right? Same idea here. Let's dive in and see how this works. So, check out our toolkit. For big stuff, like the length of a room, you've got your trusty measuring tape. For something on your desk, a simple meter rule works fine. But what happens when we need to get smaller and smaller? Well, that's when we need more specialized, way more precise instruments. And trust me, this is where it gets really cool. Just think about it for a second. Try to picture yourself measuring the diameter of, say, a metal pipe or even a marble with a regular old ruler. You can kind of get close, maybe, but you can't get a truly accurate reading, can you? You're kind of guessing where the edge is. Your measurement is, well, it's a guess. We need to upgrade our tool. And here's our upgrade, the vernier caliper. This thing is an absolute game changer for this kind of work. It's got these jaws to grip the outside of the pipe, another set for the inside, and even this little probe that slides out to measure depth. And just look at that accuracy, 0.01 centimeters. That's 10 times more precise than a standard ruler that only shows millimeters, a huge leap. Now, learning to read one might look a little intimidating, but it's actually a pretty simple 3-step process. First, you get your main reading from the big scale. Then, and this is the clever part, you look for the one single line on the little sliding scale that lines up perfectly with a line on the main scale. You take that number, add the 2 together, and bam, you've got your measurement. It's a genius way to read between the lines. Okay, so the vernier caliper is great, but what if we need to get even more precise? I'm talking about measuring the thickness of a single strand of wire, or a single sheet of paper. Suddenly, even our fancy caliper isn't precise enough. We have to zoom in again, And for that job, we bring out the big guns, the micrometer screw gauge. This is truly the next level of precision. Now, pay attention to the units here. Its accuracy is 0.01 millimeters, not centimeters, millimeters. That makes it 10 times more precise than the vernier caliper we just saw, and 100 times more precise than a regular ruler. That's incredible. And the way you read it is pretty similar in spirit. You get your main reading off the sleeve, and then you add the super fine reading from the rotating part, which is called the thimble. Put them together, and you have these incredibly tiny measurements that are absolutely essential for high-tech manufacturing and precision engineering. All right, so having all these amazing high-precision tools is one thing, but actually using them correctly, that's a whole other ballgame. There are a couple of hidden rules and common pitfalls that can totally wreck your results, even if you have the best instrument in the world. First up, let's clear up something that trips a lot of people up: the difference between accuracy and precision. They are not the same thing. Think of a dartboard. Accuracy is how close you get to the bullseye. Precision is how close your darts are to each other. You could throw 3 darts that all land right next to each other in the corner of the board. That's very precise, but it's not accurate at all. The goal, of course, is to be both precise and accurate. Okay, one of the biggest enemies of accuracy is this sneaky little problem called zero error. Basically, it's when your instrument doesn't actually read 0 when it should be 0. Imagine you close your micrometer all the way, and instead of reading 0.00, it reads 0.02 millimeters. That means every single measurement you take from now on is going to be off by that much, unless you remember to correct for it. Let's make this super clear with a quick example. Let's say you measure a wire, and you look at the micrometer, and it reads 2.50 millimeters. Okay, that's your observed reading. That's what the tool is telling you. But you were paying attention, so you checked for a zero error before you started. And you found that when it's fully closed, the micrometer reads plus 0.02 millimeters. That's a positive zero error. It means the instrument is starting a little bit ahead of the actual zero mark, so every measurement it gives you is going to be too high by that tiny amount. So the crucial final step is to correct for it. It's simple math. You take your observed reading, the 2.50 millimeters, and you subtract that positive zero error of 0.02. Your actual true reading is 2.48 millimeters. See? If you had ignored that tiny little error, your measurement would have been wrong. It would have been inaccurate. So after all that, you might be wondering, why go to all this trouble? Why does 1/100th of a millimeter even matter? Well, it matters because this language of measurement we've been talking about, it's what builds our entire modern world. Think about it. Every time a doctor gives an exact dose of medicine in an injection, every time an engineer designs a piston for a car engine that has to fit perfectly, every time a new smartphone is built with millions of microscopic parts, all of it relies on the very principles we've just talked about. This isn't just some boring textbook exercise. Precise, accurate measurement is about safety, it's about making things work, and it's about pushing innovation forward. So we started this journey by learning how to define the world with just a few basic units. From there, we invented tools to measure the world we can see with absolutely incredible precision. It really leaves you with one big final question, doesn't it? What happens next? What new discoveries will we make? What incredible things will we build when we finally invent the tools to measure the things we can't even see yet?